Today we are going to attempt to finish 5.7 and get a start on 5.8, which again is the last of the sections of chapter 5 that will be on our test. Miss Rice said she made a practice test, which let's see if we can figure that out. Let's see, AP College Board. AP, sure. Let's see. Good morning, Edgar. Come on in. Which is leading me to believe that we will probably be making a Chapter 5 test that is on the College Board website, which for some of us is a good thing, some of us maybe not, I don't know. Let's see what we got. Progress checks. She just texted me last night that she had made it, so I didn't look at it last night. Let's see. I'm not a fan of the College Board website in terms of new progress check. Okay, whatever, I don't care. Results. It's just very non-intuitive. Question bank, maybe? Every time I'm in here, I have to remember where stuff is. Okay, I get it. I don't care. Oh, here we go. So, AP Calculus AB Chapter 5 practice test. Let's see what it looks like. Can you guys see this? Is this assigned to you guys? She said she assigned it to both of you. 17 questions. Ooh. Finding an inverse. Holy guacamole. You get it. You're excited. Okay, cool. Little U sub stuff. Yeah, this looks fun. So my thought is that this will probably be acting as our review assignment for the test, which again, I'm thinking will probably be Wednesday, Thursday next week. This is what we're going to get into today a little bit, hopefully. A kitten weighs 85 grams, huh? Cool. Okay, so that should be accessible to you on the College Board website, if that is something that you want to get going. I downloaded this app on my, or I guess it's a Chrome extension that just changes random words into Spanish as you browse the internet. So I'm trying to stay up on my Espanol. Check on their AP Classroom Tarea page. It's not a perfect translation. So yeah, this I believe has been published and is there for you. Okay, but let's try to put a lid on chapter 5. So we're gonna kind of skip the graphs of the arc secant and arc cosecant, or the inverse secant and the inverse cosecant, and we're just going to focus on the derivatives because that's sort of our main thing we care about. If you look in the book, and I do urge you to spend a little bit of time kind of reading through the book to get a feel for what the graphs are. The domain restrictions necessary are a little bit funky. So I would definitely look into that. And this was brought up, let me share. Mr. Scheer pointed this out yesterday. that I have not made explicitly clear, that when we're working with the, what am I trying to do here? The inverse trig functions, any of the function values of the inverse trig functions need to be in the domain of the restricted domain of the function that it is the inverse of. And so I think that came up yesterday when I was fumbling through the, was it the inverse cotangent maybe? Where did my notes go? Yeah. That when we were trying to identify the angle that produced the angle that produced a cotangent of -1, my brain jumped to -π/4. And then Nate said, whoa, and that was making some weird stuff happen with our graph. And then Nathan was like, well, that's not in our range, which again, it feels weird to restrict a range, but the range restriction is because of the domain restriction. And so a decent chunk of your assignment for 5.7 was just evaluating inverse trig functions. And that's sort of the main difficulty of those problems, is thinking to yourself, what is the domain restriction that we put in place, and how does that affect what values these inverse trig functions can produce? Okay, the values or the range possible for our inverse trig functions is determined by the domain of the trig function, which you start thinking about too much and it gets a little complicated in your head. But the possible values that can be produced by our inverse trig functions are restricted by the domain that we restricted on our original function. So just kind of keeping that in your brains as you work through some of the homework. Because then in the secant and cosecant inverses, which we will not be graphing, sort of a bizarro restriction that they have to make to create the desired monotonic function. So for example, the secant, they create the restriction from 0 to π/2, and then from pi to 3π/2. And so your resulting inverse is sort of a bizarro segmented thing like that. Okay. But we're going to jump straight into figuring out what's the derivative of this thing. So again, I would spend a little bit of time, just read through this in the book, but we're not going to focus too much energy on that today. So let's open up our notes where we left off. We're going to do the derivation of the inverse secant derivative, but we will not derive the inverse cosecant derivative since it follows pretty closely with inverse secant. And then we'll jump into 5.8. Yeah, we can do some Algebra 2 finance too if you want. Home loans, it's good stuff. Rip the pages out. Here we go. Here we go. This will be 5.7 finally concluded. 5.7 concluded. Hopefully, we should get through it. So today we're looking at what is the derivative of y equals the inverse secant of x. And this is going to proceed much in a similar fashion to our previous looks at derivatives of inverse trig, where we're going to try to sort of muscle this and run into a definition of a derivative that involves our function, which is kind of a no-no. And so we're going to have to sort of pull some trig identity magic to make that derivative into something useful to us. And so it starts the same way, that if y is the inverse secant of x, that necessarily means that x must be equal to the regular secant of y. And then we'll differentiate this equation and see what happens. And we're going to differentiate that expression or equation with respect to x. Well, the derivative of x with respect to x is just 1. The derivative of the secant with respect to x is secant tangent. But then because y is a function of x, the chain rule says that a dy dx spits out. And so our desired function, derivative, dy dx, must be equal to 1 over the secant tangent. And so we've arrived at this now somewhat familiar spot where our derivative has been sort of found, but it's not a terribly useful form. And so we need to go figure out how we can make secant y, tangent y into functions of x explicitly. Well, one of them kind of jumps off, hopefully, the page that we can deal with. We know what the secant of y is. We started this problem by saying that the secant of y must be equal to x if, in fact, y is equal to the inverse secant of x. And so right away, we can substitute that in. X times the tangent of y. We're like halfway resolved, but we want to be full way resolved. So we go back to our friend Pythagoras. He never lets us down. Cosine squared y plus the sine squared y is equal to 1. Which, if we divide everything by the cosine, gives us that divide everything by the cosine squared, gives us that 1 plus the tangent squared is equal to the secant squared. Okay. I quite honestly do not have these secondary identities memorized. I literally do this every time. I just start from cosine squared plus sine squared equals 1 and manipulate it how I need to. Okay. As I get older, my memory gets worse, and this is not an identity that sticks in my brain. This one is always there because it's Pythagoras. So really, it's just, I remember Pythagoras. Okay. How does this help us? Well, now we got something to play with the tangent. Specifically, the tangent squared is equal to the secant squared minus 1. Well, we don't really care about the tangent squared. We care about the tangent. So the tangent of y is equal to the square root of the secant squared minus 1. And we're like, yeah, we redefined it. Let's go plug it in. But then we're like, oh. But we just kind of like plugged one hole and created another one. You guys ever see Vegas Vacation? There's a scene where Chevy Chase's character and his family go to the Hoover Dam, and there's a leak, and he puts his finger in it, and then another one springs. He puts his finger in that one, and soon the whole wall is just leaking. Kind of picturing that. This doesn't help us, because now we still have a y here. But what do we know the secant of y to be? Oh, that's just x. So really the tangent of y is the square root of x squared minus 1. Oh, happy day. And so now this becomes 1 over x times the square root of x squared minus 1. That is the derivative of the inverse secant. Kind of cool. Or more generally, that the derivative with respect to x of the inverse secant of u, where u is some function of x, is equal to 1 over u times the square root of u squared minus 1 times the derivative of u. And then, as I said, the inverse cosecant we're not going to derive, but it follows a very similar path and eventually gets us to that the derivative of the inverse cosecant of some function u is equal to the opposite of this guy. The opposite of 1 over u times the square root of u squared minus 1 times the derivative of u. And should be an example of this, probably. Which one do we want to do? Example 7. I don't know. Yeah, why not? Example 7. Oh, goodness gracious. Thank you. Hopefully he hasn't been there long. My apologies, Mr. Lopez. I was so caught up in the wonder of calculus that I did not have a moment to look up and see your name flashing in the waiting room. That's how it is sometimes. You just get swept up. Okay, so let's do a quick example, and then we'll move on to 5.8. Woo! Moving right along. Example 7. Example 7. Find, as if it has been lost, f prime of x if f of x is equal to x times the inverse secant of 1 over x. Okay. So f prime of x. Well, it's kind of a nasty little thing. It's a little product rule. So we'll take the derivative of the first thing, x, times the second thing. The derivative of x is 1, times the second thing is just inverse secant of 1 over x, plus the second thing, plus the first thing times the derivative of the second thing. Well, gross, but I guess we can do this. So the derivative of the inverse secant is this guy. Here, though, we do have a u. So we are going to have to do the chain rule here, but, you know, we're dolphins. We can handle this. So this becomes 1. I'm going to do brackets here just to keep it separate for now. 1 over u, just being clear, this is u, 1 over x. So 1 over x times the square root. U squared is 1 over x squared minus 1. And then we need the derivative of u. The derivative of 1 over x is a negative 1 over x squared. I think I did that right. Yeah, x to the negative 1, drop down to the negative 1. Yeah, okay. Yeah. Let's try to like make some sense of this. My brain is saying, let's throw this x up there. Sure. So this turns into inverse secant of 1 over x plus, so this 1 over x is going to go, that's the official math move. It's see what I'm doing? Just flipping it over. We don't like fractions and denominators. That's weird. I can go, and it's going to multiply with that x, which I believe gives us an x squared up top. On the bottom, we've got the square root of 1 over x squared. This is kind of gross and cramped, but we're making it work. Times negative 1 over x squared. But that's kind of nice because then x squared, yes please. Boom, boom. And then we get the inverse secant of 1 over x. I'm going to go ahead and turn this into a subtraction because it's negative, minus just 1 over the square root of 1 over x squared minus 1. Let's see if the book goes any further. Yeah, they get lame on us. Yeah, this is actually going to come up in the next lesson, so might as well get comfortable with it. There is some trickeration that can happen here inside this square root. So let's trickerate. But let's just see if we can simplify that. Honestly, if you get here, I'd be kind of like, yeah, that's fine. But, you know, Louis Lighthold, in all of his wisdom, said we should keep going. And here's how we can keep going. Who's Louis Lighthold? He's the guy who wrote your book. Minus 1 over, we're going to create a common denominator here by multiplying or turning this 1 into an x squared over x squared. So it's still 1, just it's kind of disguised, which then gives us the square root of 1 minus x squared over x squared. Are we okay with what I just did? I turned the 1 into an x squared over x squared, which gave us a common denominator. The numerator was 1 minus x squared, and then, you know, we combine the denominator. Cool? So how does that help us? Well, now we can break this into separate square roots. Square root of the numerator, square root of the denominator. Oh, you dirty dog. Louis. Inverse secant of 1 over x minus 1 over the square root of 1 minus x squared. What's the square root of x squared? Careful, careful. Square root of x squared. Before you get to the plus or minus. Absolute value of x. So then our final answer is the inverse secant of 1 over x minus the absolute value of x divided by the square root of 1 minus x squared. And I'm going to call that good. Good stuff. Good stuff. we're now equipped to like tackle just about any, well, no, this is now full stop. You've now got the tools to do any derivative you're ever going to see on the AB AP exam. Pretty cool. Think about where we've come from. We started out with just polynomials, because that was kind of all we could do. We started throwing some rational stuff in there. And we kind of just stayed there for a while. Oh, we threw some trig stuff in there. And now we've got logarithmic, we've got exponential, we've got inverse trigonometric. The world is our oyster. Throw any function at us, and not any, because we're skipping the hyperbolic. That's 5.9. But pretty much any function you throw at us, and we could say, yeah, I can tell you how that function is changing. Yeah, kind of cool. So the flip side of this stuff is the integral. Didn't think we'd get away without doing some integration on inverse trig.
Mr. Smith.
Miss Basansony.
Yeah, that was right. Can I just ask a quick question? On the bookwork for 5.7,
Yes.
numbers 7 and 11 gave us functions that, like function values that weren't on the unit circle. So like, for instance, number 11 was the inverse tan of -2. Do you want us to just plug that into our calculator? Like, how do you want us to?
You would have to think to yourself, when is the tangent, or when is the sine double the cosine, right?
Okay.
Or does
Yes.
that not make sense? Sean?
What I did in work out, I just drew out a right triangle and then I solved for the missing side using the Python theorem.
Okay.
And then using that, I used the control.
Did you hear that, Kat?
Yeah, I did that on number 7, but whatever. Okay, I'll figure out number 11. Thank you.
If we have time at the end or tomorrow, we can take a closer look at that.
Okay.
7 and 11, you said?
Yes.
Oh, I was thinking of the secant. Yeah, okay. Okay, 5.8. Let's do this, or at least let's start this. How long do we have? 30 minutes? Yeah, we got this. We doing this. I'm gonna skip a page, maybe. Yeah. Homework questions. Actually, it's not integration on the inverse trig functions. It's integration on things that yield the inverse trig function, which is where we get our kind of unwieldy title. So I think it's kind of unwieldy. 5.8. Integrals yielding. All right. I always confuse yielding with wielding. You wield a weapon, right? You don't yield a weapon. Okay. But you yield to like oncoming traffic, right? It's kind of weird. Because sometimes yield means like produce, and sometimes yield means like, I don't know. English, man. Funky stuff. Yielding inverse trigonometric functions. So I'm guessing that in this case, this is not like the meaning of yield that means to sort of pause and allow somebody to go, but means like, oh, the field yielded a good crop that year, produced. So integrals producing, okay. Producing inverse trig functions. That makes a little more sense to my peanut brain. Here we go. Yielding. So there's basically 3 that we're going to dress up a little bit. So we're going to do, we're going to make 2 little columns here. So just so you know, plan a little bit. The first column is going to be somewhat obvious from our derivatives of sine, tangent, and secant inverses. So just to kind of like refresh your memory, the inverse sine produced this as its derivative. The inverse tangent produced this as its derivative. And as we just saw moments ago, the inverse secant produced this as its derivative. And so basically, anytime we're integrating something that looks like that, or that, it's going to give us the inverse secant, inverse tangent, or inverse sine, respectively. And that should be somewhat intuitive and obvious. And that's what the left column is going to say. That the integral of 1 divided by the square root of 1 minus u squared du, which one does that look like? Looks like, no, it's not the secant. No, it's not the tangent. Oh, that looks like inverse sine. So I'm guessing if we run across that and we integrate it, it's probably going to give us the inverse sine. And that's exactly what it does. You integrate that bad boy, you're going to get inverse sine of u plus c. Cool. And in like manner, if you're walking down the street and you bump into something that looks like 1 over 1 plus u squared, and you're like, hey, let's differentiate, or sorry, let's integrate. That's going to produce the inverse tangent of u. And finally, if you end up integrating with 1 over u times the square root of u squared minus 1 du, that turns into our new friend, the inverse secant of u. And these are very straightforward proofs that if you differentiate the right side, it gives you the integrand on the left side. And that was sort of the first way that we convinced ourselves when we were learning integration that a given integral that we computed was actually correct, was that, hey, if you take the derivative, you should get back to where you started. If you take the derivative of the right side of all three of these, you're going to get the integrand. So just that part. Well, these are sort of very specific cases where 1 is involved, but sometimes we're going to want to do this when these differences or sums of squares are not involving 1. So that's going to be a little bit trickier. And so the right column is going to lay out the roadmap for those situations. And so what I'm talking about is, suppose we had the integral of 1 over the square root, and now instead of 1 minus u squared, what if we just had any old square there, or any old number, really, that we call a squared minus u squared. This certainly looks similar enough to this that we assume that there is some sort of inverse sign as the integral, but it's obviously going to have to be altered because of this difference between the 1 and whatever a is. And the way that there needs to be a du here, we account for this is that this is the inverse sign. Instead of just u, it's going to be u over a plus c. And in a moment, we will verify this by differentiating and confirming that differentiating this does produce this integrand. Sort of transforming the other two, if we have an integrand that looks like 1 over a squared plus u squared. So these a's are just constants, okay? They're numbers, they're not functions. Du. Again, this feels like it should produce some sort of inverse tangent, But we again need to account for the a in there. And so this turns into 1 divided by a times the inverse tangent of u divided by a plus c. And then finally with our inverse secant, we have u times the square root of u squared. But instead of just subtracting 1, if we wanted some other number, called a squared, this will give us 1 over a times the inverse secant of u over a plus c. Mr. Smith? Get those down. So the difference between the left and the right is this a. And we'll see a numerical example in just a minute, if we have time, that we're not restricted any longer to this 1 plus u squared or 1 minus u squared. This could be like 9 minus u squared, okay, in which case our a would be 3. So we can expand our ability to integrate certain situations with these guys here. So let's do a quick proof on maybe these first two. I'm not doing the left side because hopefully you can just sort of visually see with your brains like, okay, yeah, the derivative of inverse sine is 1 over square root of 1 minus u squared. These ones are a little less clear. So let's do maybe the inverse sine and the inverse tangent. Proofs or check for right column. We're going to differentiate with respect to x, the right side. What is the derivative of the inverse sine of u divided by a plus c? Well, the derivative of the inverse sine is 1 over the square root of 1 minus this guy squared. 1 minus u over a squared times the derivative of this thing. Well, the derivative of u over a, where a is just some constant, is just 1 over, oh yeah, sorry. We're gonna just do the simple case here. We're gonna just say that u is equal to x. We're gonna keep this the simplest version, just to not overwhelm our senses. So now in this case, differentiating x over a, it's clear to see that we get 1 over a. Again, a is just some constant. So the derivative of x divided by a with respect to x is just 1 over a. The c is just some constant of integration. When we differentiate that, we get 0. Okay, so we're trying to end up with 1 over the square root of a squared minus u squared. It doesn't look like that, so let's see if we can trickerate. Down below, let's maybe combine this. Let's write it first as a times the square root of 1 minus x squared over a squared. Oh, I left out that detail. This will become obvious why I'm about to say this in a moment, but in all three of these, A has to be positive. A has to be positive. A has to be positive. Okay. So now we're kind of getting closer. We're going to pull that trick that we did at the end of example 7, but we're going to combine this and see what happens. Let's give us 1 over A times the square root. If we want to combine this, we can turn the 1 into an A squared over an A squared, which allows us to write it as A squared minus X squared divided by A squared. And we're thinking, okay, now we kind of see the greener pasture here. Let's check out this. This turns into 1 over A times the square root of A squared minus X squared divided by the square root of A squared. I just separated this radical into its two quotient parts. And then the thing I just said about A always being positive, generally if we take the square root of A squared, we get the absolute value of A. But because we have restricted A to be positive, what's the absolute value of A if A is positive? That's just A. And so we can just straight up cancel out A and the square root of A squared. And oh, happy day, we get the integrand, 1 over A squared minus X squared. Cool. And then we'll do tangent. Tangent actually goes a little smoother. Derivative with respect to X of the inverse tangent of, 1 over A. So we're going to differentiate the right side. 1 over A times the inverse tangent of, we're going to do X over A again to keep it simple, plus C. 1 over A, just a constant. Don't need to worry about that. Leave the 1 over A out front. The derivative of the tangent, the inverse tangent, is 1 divided by 1 plus U squared. In this case, U is X over A. Again, we need to differentiate the U, which again gives us a 1 over A. And then the derivative of C is 0. Cool. The 1 over A squared, 1 over A is multiplied to give you A squared in your denominator times 1 plus X squared over A squared. I suppose if you wanted, you could like combine this into a single fraction and then cancel out. But my brain is looking at this and saying, why don't we just distribute? Because if we distribute, A squared times 1 is A squared. A squared times X squared over A squared, those A squareds cancel out, and you get X squared, which is precisely what we wanted. A squared plus U squared. Cool. So now, does this give us time? This might give us time. Yeah, we're gonna go. So we'll do kind of a softball example to get our feet wet, and then we'll do an example where you'll kind of be like, "Are you kidding me?" And I'll be like, "No, I'm not kidding you. I never kid." Okay. But you know, that's life. So, example 1. How does this work? Carefully, that's how it works. The integral of dx diviso a the square root of 4 minus 9x squared. Okay. So we're like just getting used to this, but we need to start sort of being able to identify which case this seems like. Well, we've got a difference of squares. So that sort of rules out the tangent, because the tangent is a sum of squares. So I'm thinking sine or secant. I don't see anything obvious out front that could turn into like a secant situation. So I'm thinking this is going to be a sine situation, inverse sine. But we need to be able to identify. So this is going to be like a 1 over square root of a squared minus u squared situation. We need to figure out what a and u are. And so I think doing this next step is exceedingly helpful. Let's try to turn each part of this difference, the 4 and the 9x squared, into a squared expression. So what's a way that we could write the 4 as something being squared? 2 squared. How about 9x squared? 3x squared. This should sort of give you some flashbacks to maybe like SOAP. I remember doing SOAP, difference of cubes, identifying the a and b. We're identifying the a and the u. So the a here is going to be our 2. The u is 3x. And because we're integrating here, this is going to involve a u sub. But it's a pretty straightforward one. That du is equal to 3 dx, or that dx is equal to 1/3 du. And we can transform this guy, do a few things at once here. You'll be fine. I'm going to replace the dx with 1/3 du. I'm going to hold this 1/3 out front. I'm going to keep the 2 squared as just 2 squared. Just identifying what that a is. Then I'm going to replace the 3x with the u. Okay. Well, now this looks like this. And we know from the previous page that this should turn into the inverse sine of u divided by a plus c. Okay, well, we're equipped to do that now. This will turn into 1/3 times the inverse sine. We'll keep it u for now. We'll sub it back in a second. U, our a, we identified was 2. Divided by 2 plus c. And then the final sub back in for u gets us to 1/3 inverse sine of 3/2 x plus c. The u was 3x, it turned into 3/2 x. Okay, and that should feel pretty doable. That should feel pretty like, yeah, okay. So identifying the a and the u, figuring out which formula we're going to apply, following the rules. And if that's where things stayed, we'd be like, yeah, okay, 5.8, we got this. But then they kind of like turn up the volume to bat crap crazy, okay? There's another way to put it. Like, we're gonna do example 2, and you're not gonna like it. I didn't like it. But, you know, sometimes in life, you gotta do things you don't necessarily want to do, but it's good for you nonetheless. character building or something. So what I'm talking about here is something that like looks like the integral of dx divided by 3x squared minus 2x plus 5. Smithers? What? Doesn't look anything like anything on the first page. And so your brain immediately goes to like, well, could we like do like power rule here? Because this is like raise the negative first, but you're like, oh, negative first means yields a natural log, but then we need to do a u sub, and there's nothing really to work with there. What? This is just something we don't know how to do. Well, that's a deep subject. This is a quadratic. And quadratics have this like kind of interesting feature where we can always turn them into perfect squares. If we're really driven to do it, if we're just like really want to punish ourselves, there's this process called completing the square. Yeah. Remember when you learned that in Algebra 2, maybe Algebra 1, you're like, I don't ever want to do this again. And the teacher was like, yeah, we don't ever want to see you do this again. And you kind of forgot about it. Well, the ghosts of math courses past are coming to haunt you. We're going to complete the square. Oh, yep. But we can do it. We're dolphins, and we got 10 minutes to do it. We got it. Complete the square. Why are we going to complete the square? Because if we end up with one thing squared plus another thing squared, which is what completing the square will eventually lead us to, then we can apply the inverse tangent. Sort of the important feature of completing the square that's going to come into handy. And they don't even pull any punches here. Like this is a hard completing the square problem. Like non-1 leading coefficient, like it's nasty. To complete the square, we're going to take b divided by 2 and square it. Okay, that'll come into play in a second. But this is kind of the main effect that we need to remember. So what does this look like? It looks like separating our quadratic into 3x squared minus 2x plus 5. And in order to complete the square, we need a leading coefficient that is 1. We do not have. So we're going to have to factor out a 3 to give us x squared minus 2/3 x plus some blank here, some blank there, and then still adding 5. So we're kind of breaking this into like this little thing over here. Gross. So this is where the b divided by 2 squared comes into play. In order to complete the square, we're going to take this middle coefficient, this 2/3, we're going to divide it by 2 and then square it. So negative 2/3 divided by 2 is like negative 1/3, right? If you have 2/3 and you split it in half, you get 1/3. That makes sense in my brain. Squaring a negative 1/3 gives you a positive 1/9. Okay. And remember when I said this problem was nasty? You would be like, oh, okay, yeah. So this is kind of coming back. You add 1/9, and then so we subtract 1/9 so that nothing actually changes. But quick pause. Are we actually adding 1/9 here? What are we actually adding? 1/3. Can't forget about this 3 out front. Did I mention this problem sucks? Yeah, it sucks. Okay. So this 1/9, because it gets distributed with this 3, is actually a 1/3. And so to correct the adding of a 1/3, we need to subtract a 1/3. Whew. Okay, we can do this. We can do this. We're almost there. That was the hard part, I think. Why did we do that? Because now we can break this into a perfect square. Specifically, that this is 3 times x minus 1/3 squared over here, 5 minus 1/3, there's like 15 thirds in 5, right? So 15 thirds take away 1/3, I think it's like 14 thirds. Okay, okay.
Mr. Smith?
Sorry, plus, yes. Plus, plus, plus. But then this is not quite right, because we really just want the square thing, the u squared by itself, and the a squared by itself. And this 3 is sort of jacking us up a little bit. And so we're going to factor out the 3. We're going to factor out the 3 from everything, which will leave us with x minus 1/3 squared. When you divide out the 3 from 14 thirds, you end up with 14 ninths. And now finally, we are semi-prepared to do this. Okay, because this is going to be our u. This is going to be our a squared. So we have u squared plus a squared. We can do inverse tangent. Yuck. Yeah, didn't say it was going to be fun. So this turns into the integral of dx. So we did all that work so that we could rewrite 3x squared minus 2x plus 5 as 3 times x minus 1/3 squared plus 14 ninths. So let's formally define u and a. Probably easiest to start with a squared. Say that a squared is equal to 14 ninths. So that a then is equal to the square root of 14 divided by 3. U is x minus 1/3. It's pretty friendly because then du is just dx. Du is just dx. So then we'll do all of our subs. I'm going to pull this 1/3 out front. It really has nothing to do with what's going on. And so we'll get 1/3 times the integral. Dx we said was du. X minus 1/3 is our u. And then we're going to write 14 ninths as the square root of 14 thirds squared. Square root of 14 thirds squared. And now we can apply the inverse tangent formula. This guy here. So 1 over a times the inverse tangent of u over a plus c. So this is 1/3, which is the 1/3 from the front of our integral, times 1 over a. Our a here is square root of 14 divided by 3, times the inverse tangent of u divided by a, that same square root of 14 divided by 3, plus c. And then we're basically just simplifying this. So this was the terrible part. Once you've got the u and the a, you're just plugging into a formula, which is not all that mentally difficult. So 1/3 times 3 over the square root of 14 times the inverse tangent of, let's plug back in for u. U was x minus 1/3 divided by the square root of 14 plus C. And then I think I'm cool just leaving this as 1 over the square root of 14 times the inverse tangent of, let's call this 3x minus 1 divided by the square root of 14. I don't know if the book does more than that. I would be kind of okay with that. Yeah. Oh, sorry. So yeah, that was, you know, probably about as miserable as advertised. But that's that. Just before the bell, tomorrow we'll sort of wrap up 5.8, tackle any homework questions, maybe start the trapezoidal rule, but we're pretty much done with all of our material. What? That happened fast. Uh-oh.
Mr. Smith.
Flash an orange box. If you are done, you are done. Will our test be the same format as the practice test? Probably. I haven't decided yet, but probably. Yes, take a look at the practice test tonight. Continue to work through 5.7 assignment. If you're really looking for something to do, try 5.8 homework. I think you also have some FRQs to be working on, so there is no shortage of things for you to be doing in this class right now. You decide what to be working on.
Mr.
All
Smith,
right. Yes.
can you go back to the check part for the inverse sine, please?
Yeah. There you go. Great day.